Okay, so today we're going to sort of do a little bit of coding example. What we're going to try to do, so normally for your homeworks, we give you the solution and all you're doing is filling in a few library functions. But maybe that doesn't help you so much if you have to actually write code for your gadget, which we can't give you the solution for because we have no idea what your gadget's going to do. So we're going to make a glowy thermometer and sort of poke at that main file to try to get things working. I think we've looked at most people's schematics. If you haven't gotten comments, let us know. We're starting to look at the ones that have been resubmitted. Generally, when we stop complaining, that's usually a good time to work on your layout because that's also due, I think, Friday. So you want to get started placing parts, but try to get the okay from us before you go crazy, lay it all out, and then we tell you that your MOSFETs are hooked up backwards, so that you have to disconnect all your traces. One other thing that I'm seeing, so there's sort of 4 solutions for power that most mini gadgets are using. The first is to use the coin cell that's on your mini gadget. And so if you're doing a super portable, very low power device that's not going to be on very much, that's perfectly fine. And that is, I think, that BA2450 battery. So you can use that. There's a lot of people are going to be using AA batteries, like a 4-pack of AA batteries. Like I think SparkFun sells a little holder for that. And for those, we're recommending you either use a 2-pin or 3-pin header. If you're only going to use a 2-pin header, I really recommend you use a polarized one so that you do not plug your battery in backwards and blow something up. And as well, I think we sort of warn people who are doing that, you need a voltage regulator so that you don't give more than 5 volts to your 1890. The third option, some people are doing is wall power. Your life is much easier if you just use like a cell phone charger style 5-volt adapter, because you kind of want 5 volts or less, and you can just get 5 volts at 500 milliamps or 1 amp for like $3. I mean, those 5-volt chargers, like any of them on like Amazon, are very cheap, and they come with cables. The only detail is that we have a mini USB cable, not a micro USB cable, because micro USB is really flimsy and probably harder to solder than a mini USB. If you're using a higher voltage, you definitely need a voltage regulator. You may not need one if you're doing just the 5-volt wall adapter for charging cell phones. And finally, the fourth option that some people have sort of stumbled across is there is a different battery in there, and it is the BA16850. It is a lithium battery pack that's actually bigger. It's like a giant AA battery, and it's kind of funny. So if you needed something that had a really high capacity and has like multiple amp hours at 4 volts, like it's perfect. But you have to be aware it's much larger. You may have noticed this already if you're in layout. And we're going to talk about where to get those. We want you to make sure that you buy a protected battery, because otherwise, when you discharge it, rather than stop going it, when you try to charge it again, it will just catch on fire, which is bad. And it's like $1 more for a protected cell. And we just want you to be aware that you grabbed that on purpose, and you didn't want the coin cell to grab this other lithium battery. So there are 2 lithium battery packs basically in the gadget library. So make sure you know which one you're using and that you actually want to do. Okay. Is that better or worse?
Is it better to see the text in white or the background in white? I'm trying to make it bigger too, but
It's green? Oh, I see that. Maybe white.
background text bold. Okay, I'll try my best. I've never actually had to change this. So.
Can I see it back?
It should make common sense.
Is this a lot better?
Yeah, but because it's italic. Doesn't seem to actually do it.
Or just hit Control A and
That
that wasn't it. mean, it's not bad. Maybe it's harder for you to read than it is for us.
That's not hard for me to read.
We'll change the font.
I'm
Are
trying to
people,
do
actually,
anything.
are people having trouble reading this?
Is it okay? Like, can people in the back row read this? Or is it, yeah, okay. All right.
If you're not happy with it.
You could always
You
move up.
could always sit up in the front, there's plenty of room. Okay, so apparently we're gonna start by giving you what it does.
Well, no, this is the example from Light Makes Me Blink. And so, this is a reminder of like, you probably looked through the main file of Light Makes Me Blink and the Sleeper Glow one to see what it was doing. Maybe you didn't, maybe you just edited the MG2 library file. But if you did, you may have noticed a certain structure to these main files. And so today's tutorial is really, we're going to cover a few things about like variables, loops, if statements. Sorry if that's like overkill for some of you. And we're also going to talk about the structure of these kinds of files, of main files and of library files. So just going through this and thinking about what we may need in a new file. There's the include for an mg2.h file. So what is that? That is a header file. And this is pretty standard C stuff. And the header file defines the functions that are in mg2.c. And it also has some pound defines that apply to the whole program.
And it was a super fancy header file, right? All these would have like comments and all kinds of stuff explaining this, because this is what, this is not really for release, but if you went to someone who did like programming all day, every day, that's where all the details would be. But basically the really important stuff that makes your gadget actually go is that avrio.h and that delay. So every time you use the delay function, if you don't have that included delay, it doesn't work, it gives you an error. And if you don't have avrio, it has no idea what a port is, it has no idea what PB4 is. That's where all that stuff comes from, like OCR1A, that's where all those secret variables are defined, they're in avrio. And if you ever actually try to find avrio, it's actually just redirecting you to like 97 other files for whether it's an ATtiny 45 or an ATtiny 44, an AT-mega 328. There's just dozens of files for all the different Atmel parts, so that when you say OCR1A, depending on which chip you're in, it's maybe somewhere else in memory.
So you might be asking, how does the compiler know which chip I'm using? And that's in the make file. So if we look at the make file, the very first line that is not a comment is MCU, so microcontroller unit, equals ATtiny84, which is what you're using. So if I change this to ATtiny85, suddenly a lot of my code would break because the 85 doesn't have things like PA7, for example.
Or what's scarier is it may compile just fine,
Or
but
it
it
could
won't
do that.
work on your gadget. Very important, and I think people who are using APR Studio, if you do not either use the external make file or explicitly set this stuff up, there is the frequency of the CPU. Yours goes at 8 megahertz. And if you do not tell it this, things that rely on timing, like delay functions, they have no idea what to delay. Like 1 millisecond ends up being so many number of cycles, but if you don't tell it how many cycles there are, how is it supposed to know? So your delays end up being crazy. Your output format, you don't really want to know about that. Your target, that matters a lot. So let's say if you were me and I had to make a gadget 1 program, the first thing I would do is say, okay, I have all this working example code from before, and my thing is totally going to work like Light Makes Me Blink. So I'm just going to copy and paste Light Makes Me Blink into a new directory, and then I'm going to rename Light Makes Me Blink to like my gadget 1, .c, and like this will totally work, right? But when you go to compile it, it's going to try to compile Light Makes Me Blink. So if you are changing your code and it's still doing the same thing, you're like, why isn't it working? And it's because it's taking that other file that you haven't been changing and it's compiling that every single time. So you need to change this in the make file. We're not going to get into like how makefiles work. I don't think anyone really understands how makefiles work, to be honest.
You need to understand the syntax and the things that you can twiddle and not twiddle, but
And then the other detail is that we include MG2.0, which tells it to look for that mini-gadget.c and .h. Compile that as well, because your main program is relying on
right. So if you were to rename mg2.h and mg2.c to some other file, like my personal library or my personal gadget library, you would have to also rename it here.
And you can totally see that in gadgets past, we used to have,
There's another one.
for X megas, we give you an SD card library, which needs disk I/O, it needs a real-time clock.
Yeah.
Let's say you write a serial library. Usually you don't lump it all into some giant file that's hard to read. You just have many small files that each do what you need, and then they all end up getting put here. With fancier make files, especially for very large, complicated processors, this kind of stuff is auto-generated and done for you, but this is a very simple way to sort of put the 3 files that you're using into the make file so they're compiling correctly.
All right. So, through the assignments that you've done for the mini gadget, you already have working library code that you wrote for how to make it go to sleep, how to set software PWM on LEDs,
People are updating.
how to do analog. And so you can use all that code, and we're not going to penalize you if you've written it incorrectly. We'll probably send functioning code before your mini gadgets come in, just in the cases where your code may not be perfectly working. But what you will need to do is you'll need to make the main file and any other functions that are useful for your mini gadget. And you may also need to change the library files to adjust the code for your mini gadget. So your pound defines, where your sensors are, that kind of thing.
Yeah, so it seemed like a lot of work at the time to say, to tell you where our sensors are, let's tell you which ports they're at. But it's really nice when you have all that stuff and you say, well, actually, my thermistor is no longer on pin 2, I put mine on pin 0. Let me just change this one line of code and voila, now the code works on my gadget, as opposed to having to rewrite everything from scratch every time.
So today we're doing a tutorial that is basically, I guess the idea is, pretend that this mini gadget is a glowy temperature orb with a knob on it. So it has a knob.
Yep.
And we're going to make
Here's
it
the
into, we're going to give
photocell.
it a few different functions.
All right, so it looks like you've got the thermistor hooked up to sensor port 1.
Yeah.
And we've got the knob hooked up to sensor port 2. So probably the first thing you want to do, we're going to do, is write down where everything is so that we don't have to stare at the schematic anymore. We can just focus on the code.
So we'll probably redefine these. If you remember, sensor port 1 is on port 0, sensor 2 is on 1, and sensor 3 is on 4. So we'll actually name these temperature. You know what, actually, before I do this, let me do what Brian said earlier. So I have my light makes me blink solution. I'm going to copy this. I'm going to paste it into a new folder, and we'll call this glowy thermometer. All right, so now I have all the code from glowy thermometer. I'm going to close all these so that I don't overwrite that. And I will open my,
Okay, so why don't we first, let's rename the light makes me blink.
yeah, so I'm going to rename my main file, glowy thermometer. So this is most likely the approach you will take.
And then make file as well.
Yeah.
Just drag,
So I'm going to open all these in WinAVR. And in the make file, I'll make sure to target glowy thermometer.
And if you want to make sure that you did it right, before you start changing all the code, you see if it compiles.
So the tools make all, and it'll do its output.
So,
And it compiles, yeah. Okay. All right, so now I'll go over to this, and I'll start renaming these to be more appropriate for my particular gadget. Call this one temperature, call this one knob, and I did add a light sensor. Maybe we'll get to using that, maybe not. My init ADC and int read channel, those things are probably still fine. I may need to copy in some code from like the sleep or glow assignment because I'll probably want soft torpedo later on. So yeah, so that's still working. So here's the file as it was, the main file as it was. What is it doing? So every single gadget program is going to require this int main void. And that's just this is the function that your gadget will run. It's like the entrance point. So the first thing it does is it sets a bunch of variables to be unsigned integers. And in AVR, an unsigned integer is by default 16 bits. So that means we can hold a value between 0 and 65,535, I guess. Which is important to know because some of your values can go higher than that. So there are different integer types. Like if you wanted a version that is 32 bits, you would use an unsigned long int. Now it's 32 bits. If you want to save a little code space, you can do an unsigned short, I think.
And so you can use these. Usually they're very confusing because on every processor, especially now that we have 32 and 64-bit processors, these vary based on what you're on. So now what a lot of people do when they're writing cross code is they do things like UN of 8_t, which you might see, and that is an unsigned 8-bit. And it's very unambiguous how big that is and what it is. And they go 8, there's a 16, there's 32, 64, 128, you know. It is what it is. For your gadget, you don't really need those.
And given the 3-channel returns, I think, okay, it returns.
Yeah.
So we probably want the sensor value to be the same.
So for those of you who are not into coding, you're sort of like, well, this is all relevant, and you're right. But for people who like programming, these are some weird things. We're not trying to optimize our code space. It's okay to have 16 bits when we're only passing 8-bit things around. The world does not explode. 8 megahertz is still plenty fast enough to be wasting bytes. Now another thing about this is C code, which is venerable. And C really likes having its variables declared at the beginning of blocks. So wherever you have brackets, technically we could define new variables at the beginning of this bracket. And you actually can put brackets anywhere you want, but people really don't like it when you do that. So normally with C code, you figure out what you're going to use within a function, you declare it at the beginning, and then you go from there. If you have things that need to be used across multiple functions, then you make them global.
So you just put it outside of the function, global variable.
And also, this kind of embedded code is also a place where volatile stuff actually gets used. Like normally, if you've been writing a lot of code for assignments, almost everybody you're like static blah, static blah, static. And here you actually use volatiles. Yeah. Because if you're going to write code that uses an interrupt to read a sensor or something, that actually is exactly what it's for. The sensor is updated mysteriously, so you can actually have your main loop that says, while sensor does not equal 37, do one thing, otherwise do something else. And somewhere else that variable is being updated.
So hopefully you remember the volatiles.
Yeah, so that's very important for this stuff, whereas if you don't tell it it's volatile, your compiler generally optimizes out those sorts of things, because it says, oh, this value is never going to be 37 because I never set it for 37. And therefore, we'll just remove this whole block of code. And, your gadget stops working.
All right, so the first thing it does after it declares its variables is it initializes the system, which is a call to this function, which this function itself is just a wrapper and calls all your initialization functions that you guys wrote. So that's pretty obvious. And then after that, it waits for a button to be pressed, which is a call to a new custom function that you could write. You could make a wait for button, or you could make a bunch of different functions. We'll make a few in this demo. And it just, it waits for the button to be pressed. So pretty obvious there. And then you've got the while one. Now, I think you remember, we've mentioned this before, while ones or while true or true. Those kinds of loops, usually in computer science classes, they'll tell you never want an infinite loop. But when it comes to gadgets, you always want an infinite loop. You want an infinite loop in your program because it's quite possible that
If you reach the end,
here, it'll just keep executing old code that you have on your gadget.
I think it actually resets.
Or it may reset.
Yeah.
In either case, it's not desirable behavior. So
If you do
always
not have
wanna
an operating
some-
system, you don't go back to the desktop. It's actually kind of fun because if you actually have a segmentation fault on a gadget, you just start executing mysterious things because you've gone through the segmentation and you just keep going and you're somewhere else. As opposed to like the thing crashing and saying, we're not going to let you do this with your computer. These things are happy to just keep going. And you end up with some very unusual behavior.
All right, so what's going on in this loop? Basically, we're reading the sensors, and then we're checking what the sensor values are. And this is sort of a very simple way of figuring out what the lowest sensor value is. And whatever the lowest sensor value is, actually, it's not whatever the lowest one is. It basically checks if the sensor value is less than 250, that means you've probably got a sensor plugged into that port. And then it sets the blink time to that sensor value. And what is, so the way this, I guess this code kind of prioritizes, I'm not sure it's actually running. The way this code kind of prioritizes things is it makes sensor port 3, like if you have things plugged into multiple ports, then sensor port 3 is the one that's going to affect things.
So this is just an artifact of your homework assignment
Yeah.
where Tom figured you'd plug in your sensor into one of the ports. Maybe you wouldn't plug it into the right port, but you figure out which one you would put it in. Just work with it.
Right. And then it basically turns the LED on for a time that is a number of milliseconds that is just the blink time times 3. And remember, the blink time is just set to your sensor value. So you do a lot of this kind of sort of crazy mathematical manipulation in a lot of your programs where you're just, you're scaling like different sensor values. So what this actually does is the lowest sensor value, which corresponds to, one of your sensors, that lowest value, the lower it is, the faster your LED will blink. So that's all. You may remember that behavior, you may not, but that's all it does.
But for most of your gadgets, like this may be as complicated as you mean. I think some of you really, really want to do something way more complicated.
If you've got a PCD, it may take a little more.
Not really. But you're basically going to do this very simple thing where you're going to do some sensing, you're going to do some manipulation of the sensor values, and then you're going to output something with your sensor values. So your code should not be too complicated. And it's sort of up to you how you want to abstract your code. So for instance, here Tom just reads 3 sensors, and then he has some very simple logic here, and then he has his output function. If you want to do more complicated stuff, that's fine. But in this case, he didn't need anything. He didn't need an extra function to do something fancy. But you might want one so that you're not calling the same code multiple times.
Okay, so let's grab some of the code from the sleep or glow assignment, because we want a glowy thermometer, not just code that turns stuff on and off. So I'm basically going to merge these two. I won't do sleep, but I will do the set LED, the new init LED, maybe the new init button, because I like my button to be on an interrupt.
And the timer overflow.
Yeah, and then all the time overflow stuff. Look at that. So I'll just copy this in, and I'll get rid of certain other functions that this kind of takes care of. Like init system, I will actually modify. Oops. Okay, so this init system, I will add init ADC to this one. Hey, figured something out. I'll delete this one.
And the other init button.
And yeah, these 2 init buttons. And this set LED also. Don't need it anymore. Ah. And this could break a bunch of stuff, but like for example, I haven't merged the mg2.h files yet, so if I do a make all on this, I'm sure it'll get me a bunch of crazy stuff. So I want to add these definitions. This one.
Oh yeah, just looking for sensor and temperature, not sensor.
I don't have button pressed anymore. I don't need it, so I'm getting rid of that. I didn't copy go to sleep, so probably that's okay. And I think also there were some volatile global variables that I have to copy.
And then just in the low thermometer, that's the we have to fix something.
Oh yeah. But,
That's not gonna work.
yeah, so like sensor one declared. Right. So here, you know, I renamed all my sensor values, and it might be useful to rename the variables as well. So I'll make this one temperature, and this one knob, and this one light. And then change it here too. And then I'm just going to get like,
Now, obviously, this works because C code is case sensitive, so that does make sense. Sometimes you might want to say like temperature pin or something, but you want to disambiguate it a little bit.
and I'll just get rid of my old code because that's not what I really want to do anymore.
Let's just see if that.
Yeah, so the first thing when you're merging all that code is probably to check that it actually goes. It probably won't. So my first error, yeah, okay, so my wait for button function, I'll just chuck it for now. So I'm using the button. Yes, that's true too. So if you look here, we're actually adding, like we have a few more pound includes in the sleeper glow. Yeah, we don't need sleep.
So it's kind of a pain to merge the code, but makes your life better in the end.
Yeah, so now, yeah, okay, that's just a warning. That's fine. So this is what you do. You basically go make all and then conflicting types of set LED, probably because I'm using kind of different variables. Yeah. So the set LED was using ints before, now we're using uint types. And in the declaration, you can either give the names, like in the .h file, you can either give the variable names you're using or just delete them. It only cares about the variable types. Okay, yeah, we don't need that anymore, so, because we're not using sleep. And I think we were also doing something here that we want to change, because we're going to use that button. Yeah.
When we get
so-
the button,
Right. And, all right, we have something that compiles again. Yay.
doesn't do anything, not yet. So why don't we see what happens if we just put the 3 sensors on the LED? Does that work?
Yep. So we'll set LED to temperature, knob, and light.
This may be madness, but we'll see what it does.
And we'll hit make. And then, unfortunately, I don't have on this computer, anything to install stuff so that I can do tools program. I'll try it. Yeah. So I need to use my ISP through AVR Studio. So this is just a different way of downloading and programming most of you have set up. But, it doesn't really matter. All I'm doing is doing the program. So, any gadget, flowy thermometer.hex program. Is it all? All right, so it's mostly white because, but you can use the knob to, so here. Since it's super bright, one of the advantages is that you can actually see it. Brian is turning the knob. I will cut the light.
Oh, yeah, there we go, that's nice.
The thermometer is not going to change all that much because its operational range
But
is
you
like,
can usually squeeze them and you'll get it up to body temperature
Yeah.
quickly. And then it'll kind of go back down. All right.
so we have something which is partially working here. So we've got, you know, it may not be the most useful thing, but we're setting the red value to the temperature, the green value to the knob, and the blue value to the light sensor. And they're doing stuff. So we verify that we can do stuff. So when you're programming, don't just write everything all at once. Basically do these kinds of intermediate steps. Check that, you know, function 1 of your mini gadget works, then check the function 2.
So why don't we make, something that might be useful is why don't we make it so the knob and the button, you can go between
Different
red,
colors.
green, and blue,
Oh, yeah.
and we'll just see if we can vary all the colors.
Okay, so we'll just use the knob to, let's see. Okay, so how would we do that?
So why don't we make a function called
Yeah.
read or set color? Oh, I guess we have that.
We have set color. So I think we can have, how about we do 2 modes. One of the modes is just, you know, it will color cycle through the LED, and the other mode is it will use the knob to color cycle through the LED. So one is like automatically color cycling, and the other one is the knob will change the color manually. So we'll make 2 functions. One will be color cycle, or automatic color, whatever you want to call it, really. Auto color cycle. And this could take a parameter if you want. Why don't we make the parameter be how quickly it color cycles?
Or how long?
Yeah, how long it takes.
Yeah, so that we can make a function.
Yeah, I mean, it'll only go through one. And, yeah, you don't want to call it long. In delay. Cycle delay. Okay. And we'll make another one that's called int knob color cycle. Actually, these shouldn't be ints, they should be voids because they don't return any varied values to us. Knob color. And
Or do we take the value?
yeah, it takes the value from the knob. So it takes an unsigned int. Okay, so when it comes to functions, in C, you have an option to put a variable name here, like int or unsigned int or uint8 or whatever, and then it would have to return a value of that type. So if you have, like, for example, the read channel function returns an unsigned int, and so it's returning that value so that you can use it in another function.
Whereas every other,
Most of the other
functions don't return anything. You just do a bunch of code and then it just comes back.
So those usually have void. Okay, so if you want to cycle through a bunch of colors, usually the way I do it is I have a bunch of for loops. And I set up like 3 for loops to go from red to green to blue and back. That's the simplest way to do it that I know of. So You can do for int I equals 0. I is less than 255. Yeah, okay.
So it's spoiled by C++ and Java where you're allowed to just throw your variables down.
So we'll make an I, which is just a generic counter. I is less than 255, I plus plus. And then we're going to do set LED, 255 minus I 0. So what this does is every time it goes through the loop, it sets the LED. It starts with red 255, green 0, blue 0, so all red. And then as I increments, it'll go all the way to red 0, green 255, blue 0. And we probably don't want this to happen without a delay, because without a delay, this will happen in about a millisecond total. So we probably want to do something like delay ms, and then this is where we can put our cycle delay. If you want a little more control over it, you would do like, so if ms is 1, then it's going to take a quarter of a second to go from red to green.
So why don't we just try that function as
Okay.
and we'll just pass the null value of the cycle.
Okay.
We'll do that.
Yeah, that's a good idea. So we'll do auto color cycle, and we'll pass it knob. If I made any mistakes, fortunately not this time. Okay.
All right.
It is
so
fairly
some speed.
slow.
So faster.
Now it's only going to update once per. Okay, so now it's going super fast. Now it's going somewhat slower. So, you know, it's basically doing what we want. Actually, this is a good example of the other, the knob control.
Yep. This way I can do something. So,
Okay.
Yes, you have to sort of play with what you actually want to do. So knowing exactly what you want to do ahead of time makes it much easier to get things working. Because you have to, take the values, do some programming to them.
Okay.
Something that they were, which by with this, I wonder if I can relate to the microseconds.
Yeah. So if it's in microseconds, you're basically going to have 1,000 times more resolution. You may want to scale, like if you're taking it, if you just think about the math, right? If you're taking a value that varies from 0 to 255, you may not want to pass it, and you have underscore delay underscore microseconds in here. You may not want to pass it directly. You may want to multiply it by 200 or 300 or something like that. But you want to make sure when you do stuff like that that you're watching out not to like overrun your 16-bit variable space. You can't have numbers greater than 65,000. You may actually hit that. And if you multiply something and then divide it, if you multiply and go over, that's too much. Like, you can't just do that.
Fun things you really
Stuff that you may run into. Okay, so if I want to go from green to blue, now I make another loop right after it that does the same thing. It's just shifted over by 1. And then if I want to go from blue to red, I do the same thing. Now I can do some other cool things. I can start thinking about like maybe I want to cycle through white and through other colors as well. That is basically, we'll leave that up to you, but you can see that you can go through a bunch of different colors, and it's fun. Okay, so that should be good. Program. Okay.
All right.
And this is going to update once per while loop, once per measurement. So you could make it go really slow, or you could make it go really fast.
Yeah, I won't make it go very slow because it's going to take a long time. Now, and again, this is like almost at the end of the potentiometer. So like between way too fast and and kind of slow is like a very small amount of the knob. So what we might say is actually, we need to do some math on the knob and not just pass the value directly in. Because the knob, for instance, with the voltage divider, we're probably going to more like
0 to 20 or something. Okay, so that was fun. So, but really the purpose of this was to make an LED thermometer, not to make an LED floating on a board. So, I think our LED thermometer should include this as a mode, but that's just because I like that.
And if you remember the thermometer that I brought in, it did have all these modes. And that's because, why just have a thermometer when you can play with it?
So I guess we don't actually need knob color because auto color cycle and knob color, basically it's just a matter of sending it a fixed value or sending it the sensor value. So we don't need that, but we do want something that interprets the temperature value and spits out an LED value that's appropriate. So to do that, let's call this void set color from temperature, and we'll send it unsigned in temperature. Now, unfortunately, you guys don't have a serial interface, so you don't know what value the temperature sensor is actually giving you back. You just know that theoretically it's between 0 and 255, and maybe it's a much smaller range than that because the temperature sensor can technically vary from like -40 Celsius to 80 Celsius, and you may only care about like 10 to 30 degrees Celsius, like room temperature plus or minus 10. So we'll just sort of do a little experimenting with ranges. So we'll set up sort of the correct algorithm, and then we'll experiment with different ranges. So what's the best way to do this? The best way to do it is probably to say red is going to be too hot, or red is going to be like the hottest end of the spectrum, and blue will be the cold end of the spectrum, and green will be right in the middle. You could obviously map different colors. You could make white be hot, whatever you want. So I'm going to do something like, if the temperature is less than half the potential value, which is 127.
So why don't we use some
Oh yeah, or static. Yeah. So like in mid-range, we'll make a int hot, max heat. Make that be like 200 maybe. We could actually do it based on the mid-range. So we could make int range equal to 60 or something like that. And max heat is just range plus 60, and min heat is
Now,
minus 60.
now this photo cell, putting on a voltage divider, hotter will be smaller though.
Yeah, so hotter will be,
Small, right?
yes. So I think Brian's right. Depending on the circuit, hot will either mean that your value is actually going up or if your value is going down. So let's start with what I think is correct, which is that hotter values make the heat go, make the value
The
go down.
voltage on the sensor will decrease as it gets hotter. And that's when the sensor is on the high side of the voltage divider, that's what happens.
So if our temperature is less than the mid-range, we're in
One or the other. I'd have to do
If our temperature is less than the mid-range, we are in the zone where we want it to be, where it's hotter than normal. So we want the LED to go between green and red. So we're going to set the LED, and the blue value is going to be 0. So the red value should increase as we get closer to max heat, and we'll have to scale it. So let's see. Here. So mid-range. So for green,
we'll create a scale of temperature value, we'll just say, all right, why don't we do the math once, and we'll make a temperature from 0 to 255.
Yeah.
So we're gonna just set the LED to 255 minus temperature.
Okay. Makes sense. So we're doing our random scaling here.
Now we do it, okay, so temperature is gonna be equal to some crazy function, which is, okay, so temperature is less than,
So it's going to be mid-range minus temperature
which is the value
from, and so that value is going to be, in theory, we think, 0, like, well,
0 to negative, or 0 to 100, basically.
well, so it's 127. If we assume that max heater is our maximum range, then that's what we should be scaling off of. So if our range is 60, it's going to go from 0 to 67. It's going to go from 0 to 60, I would say. So
So multiply by.
multiply by 255 divided by 60. And that should do it, yes. Pretty sure that's correct. And actually, I think we're not even going to need these max heat in. Now we make an else statement, which is basically the inverse. So here, temperature is equal to temperature minus mid-range. And so the higher it goes, the colder it'll be. So we want to express that with more of a blue LED.
Choose the 60s range.
Oh, yeah, sorry.
So we're kind of making math and like, we don't know if this is going to be right. We have to play with the values, figure it out. If you have access, now unfortunately we don't give you guys a serial port for Gadget 1, so you can't do like the low-level printf style debugging. But you know, there's nothing stopping you from measuring the voltage on your sensor port, and then you know what the voltage is at the min and max values, and your gadget is going to convert, you know, 5 volts will be 255 or the like, and so you can actually figure out what it should be doing.
Okay, so we've got our math hopefully correct, which is, you know, so if our temperature is less than the midpoint, we're assuming that that means that it's getting hotter than the average temperature, and that means that we'll make our temperature equal to some value, like midpoint minus the temperature value times 255 divided by the range. So if our temperature is 100, if our input temperature is 100, we'll end up with something like 127 as the set LED value, which will put it right between red and green. If our temperature is right at the range, like right in the middle, then temperature minus mid-range will be 0, so our set LED will be all off on red, off on blue, all on green, which is what we want. So this sort of makes sense.
Now instead of calling our color cycle, we'll just call
So we'll call set color
color
from temperature.
How we done with the low? Okay. So let's see if that passes. Let's see what it says.
So it's kind of
Awful, mostly green.
yeah, mostly green, that makes sense.
Using technology and then squeeze it, and it kind of just gets more green.
Yeah.
So clearly we're not in the right range, because that should be red right now.
Yeah, well, it should be closer to red than, yeah. So it went from sea green to green, which means it's a little below like the midpoint until Brian pushed it, and then it got up to like the midpoint. But really, Brian's body temperature is probably more than air temperature. So let's adjust our range and make that like 40. And maybe let's adjust the midpoint also and make that, let's see, should it go down? Should it go up? Maybe 135. And let's just try again. Should it go down? Or, I think, well, we'll figure it out. I mean, to some extent, hitting make and program. Okay, so now it starts off green, and it
Now
is
it's
in
getting-
fact getting more like yellowish.
Yeah, I don't know how,
I would even, so I think the midpoint is right now, but maybe we should make the range even smaller.
yeah. Does anyone have ice cubes?
Okay.
So green.
All right.
Oh, there we go. Now sort of that pleasant orange color.
And your fingers are probably about 80 to 90 degrees, so, and we probably want it to be able to go up to 100 or 110, you know, for summer. So it's probably about the right range now. All right, so we have, this is kind of how it's done when it comes to adjusting sensor values. You just sort of have to
Yeah, so there are many,
test stuff.
and you're right, there are many different ways, right? If we had serial, like, so there are debuggers for these kind of controllers, and we could have a live debugger for people who are used to using debuggers where you can like look at values in registers, inspect them. You can also, you know, have on the other end of the electrical engineering, you could be sitting there measuring the voltage change as you're pressing on it to like figure out what the voltage actually is doing. Or in the middle, you can just sort of guess and check and say, well, it should be around here, and then I'm just going to tweak these numbers and recompile until it's right. And for your gadget, I mean, you can kind of do whatever's easiest for you and figure out what you want to do.
Okay, so one last thing I want to do is I want to use I like my auto color cycle, and I want to use the knob, or I want to use the button on the mini gadget. Many of you have buttons on your gadgets as well to cycle between them. So to do that, and to use the button in an interrupt, so I don't need to constantly be checking the button, I'll make a volatile value. Can I make it in here now? All the way?
Just put an external so just a volatile button state, or just state.
All right, yeah, it's sort of the general state.
0, and then in our .c, or way down at the interrupt, we're just going to use state equals not state.
So in this case, we're just inverting it. We only have two states, right? We have the state where we're using it as a thermometer, and the other state where we're using it as a thing that we control how fast the colors change. If you had more than two states, you might do something like state plus plus, and you know, if state gets to the maximum number of states you have, like maybe it's 5, then you make state be equal to 0 again. So there are different ways to do this, but this makes this sort of invert. So make it be either 0 or not 0. Makes the most sense when you've got just two states.
And also, this is not debouncing for our little gadget.
Yeah.
Instant, we're not going to worry about it. Now, the only other thing it has to do is your main function can't look at this value right now. It's living on the 52.h. You can either have a function that checks it, so we call this, have a function called get state. That's the nicest way to do it.
But then you still have to pull.
Uh,
Well, no, you don't have to pull. You're right.
you just have to.
Yeah. So you could make a void get button state. That's probably, yeah, that's the nicest way to do it. And then all it does is it returns state.
And so that when you start adding stuff in your C file, you have to go to your H file. So that basically,
It knows.
yeah, the way C code and a lot of code works is glowing thermometer is just looking at the .h file. The .h file is sort of its promise about what you can do with it, and the .c file is the details. And you don't look at other people's details, you just look at what they tell you you can do. So now get button state is basically published, and now you can use it in this glowing thermometer. So now you can just say, if get button state,
And I don't even need
the
to.
function.
Right, sorry.
And then he'll do auto color cycle, else he'll do set color for temperature.
And I will pad indentities because otherwise that's,
And Tom is going to use the two different styles of brackets. He's using the kind that are inline and the kind that start on the same line. We're not going to enforce style guidelines. He's using camel case. CMU still loves the underscore system for all their old stuff, I'm assuming. I doubt that's changed in 10 years. But obviously this doesn't look very much like Java code, which I think is what they teach now. Is everything Java and CS?
or
I
Python.
don't know
Java.
Java, right?
What do they do now?
SML.
Java anymore.
Okay, what are they up to? Back to C?
XML.
SML.
Well, they've always done SML.
But now they're doing more SML.
They're doing more SML, that's interesting.
Also C now.
Also what?
C without all the interesting parts.
Okay.
C, except
Not C.
really stupid.
Okay, so I guess my question, so what are they teaching 213 in?
C.
Okay, and 212 is in?
213
Doesn't
still
exist.
falls.
212 is, okay.
It's now in SML.
Okay.
Yeah, so
But
did
stage
you-
is not an int. It is not a void.
All right.
Let's just call that an intention.
Good work. Okay.
Yeah, I did have, notice there are sometimes warnings, like type defaults int in declaration of state. Because I never even called this, all I said was that it was volatile, I didn't say what kind it was.
All right.
Which is probably not a good thing to do. But it's still compiled. It allowed it, just as like, you should probably tell me what it's supposed to be.
Okay, so let's see what mode this thing starts in. Looks like it's a temperature mode.
Yep.
But if I hit the button the right number of times, there we go.
Yeah, because the button's not debounced. Now we're in glowy
We're on
LED.
glowy mode. If I yell at the button long enough,
Yeah, unfortunately, it kind of interrupts. All right, so now we should talk about how to debounce it, right? So let's debounce it.
oh, there we go.
Because that's annoying, and your user will not be happy.
Yeah, now, and again, this is another sort of problem is if you go to your main, the glowy thermometer, there are two functions here. There's auto color cycle and set color for temperature. One of them, set color for temperature, doesn't take very long to run. It runs many times per second, so it's very responsive. But auto color cycle knob is not responsive at all. It's kind of awful. So if you wanted something like that, you could think about rewriting it in such a way that the color cycling is happening automatically in a timer, and that all you're doing is telling it to start and stop. And then you can be a lot more responsive to how quickly it starts and stops.
You could also be lazy and put in like a
If button state
yeah,
changes.
inside each for loop, if get button pressed, you can break out of the for loop.
But that doesn't actually do anything. You have to save the previous state. Check.
Right.
So this starts to get really ugly if you're constantly checking to see if your button has been pressed. So instead what you do is you want to set up something that's constantly cycling your colors using interrupts, and then you're just sort of doing, you're sort of writing multiple threads. Except you don't have threads, you don't have any of these nice operating system things. I don't think we'll get into that. But it's something to think about for your gadget if you need that. But I think for the most part, most of you don't need two modes, you need one mode, and you're not trying to switch between them. But we can talk about the debouncing the button. So what's the
Right way to do it here.
usually I would have a time base.
Yeah.
Let's see. Do you have a timer running?
Yeah, we have a time is running the LEDs. So yeah, we could just hijack one of these timers.
Well, we don't even need the time, we just need to describe the counter value. There's the counter value. And it's changed. Button change.
Well, so the button interrupt is such that right now, pushing it down and then pushing it back up, that's 2 interrupts. So one thing to do is to make it so that 2 interrupts count as 1. And
Well, because
we can
check
try.
the shape. Why don't we just check whether it's gone to the right button?
Yeah.
Or versus the low button.
Okay, so yeah, so one thing to do is to check the state of the button itself. So that's if pin B and underscore BB PB2 then we do our thing. But otherwise we don't.
So normally the pin change interrupts every time your pin changes. So if it goes from 0 to 1 or 1 to 0, it will change. So what's interesting is that if I don't have a bouncy button, I will always go back to the same state.
Yeah.
So the only time I've been able to change states is when the button bounces a little and it gets an odd number of presses instead of an even number of presses. So this will sort of fix that, so at least if it doesn't bounce, it's going to work right.
Yeah, so it's only going to change the state if your level is high on that button.
So that will work a little better.
Should work better. So let's try it. Let's just see, we're all for minimalism. If this solves it, then that's all you need to do.
So we got temperature mode. All right, well that worked a lot better.
See if you can get it back.
Oh, yeah, so that worked way better. I'm sure it's still a little feisty if I...
Maybe if you really, try to break it. It seems to be
Yeah, that
pretty
seems much
safe.
happier. So using the scientific 5 button presses in a row system, it seemed to toggle 5 times. And for your gadgets, right, I mean, we want to make sure that you said what you were going to do, and you're going to do something. We'd like it to work. Hopefully you didn't design your system where you have to have 11 very complicated things all working in tandem to execute your functionality. And that, if your button, you have to press it twice sometimes to switch modes, that's maybe okay for gadget 1. Because there's sort of a lot of fun details about dealing with things that you don't normally deal with in software. All right, anything else?
Any requests?
Yeah.
Is the thing you did for debouncing works on really good for the go, if you pressed it, you get bounce twice and then switch states?
So basically, there were 2 problems with, so we actually have not addressed debouncing.
Yeah, we have.
And it just turns out that we don't have to. It seems to work just fine.
This particular button doesn't seem to bounce very much.
But what we did have is we had a bug where we had the pin change interrupt, and it will give you an interrupt every time the pin changes. When I press the button down, I got a pin change interrupt. And then when I let go of it, I get another one. So if I'm in state 0 and I want to go to state 1, I have to either hold the button down forever or hit it a bunch of times and hope that I get a bounce and get out of it.
So we didn't end up addressing debouncing really. One way to address debouncing is to take a timer. You probably have a timer for your LED already, and you can do something in here, you could have a counter within the timer that counts every time you overflow to get to some reasonable value. And I guess.
Yeah, so what you would do is, in your overflow vector, do we have it?
Yes, here.
What we would do is we just, in our button, we would say so in your button code, let's change it.
Why don't we just do it? So I need a
So we
volatile,
have
right?
state and add a,
Bounce.
call it or button or press or change. Yeah, pin change, doesn't matter, I don't care. Okay, so now we have volatile pin change. Now in our button code, we're going to have it, instead of state equals not state, we're just going to say pin change equals 1. now what happened is our button is basically just saying, hey, the pin should change, probably. And then in our overflow, we're going to say, if pin change, one, pin change equals 0, that's very important, or it will never happen again, you can brackets. And now we're going to do state equals not state.
Oh, in here.
Yep. So what we've done is, so debouncing, there's some hardware logic you could do, but fundamentally you just want to say, if someone presses the button 68 times in 6 milliseconds, that's probably nonsense. So what we're going to do instead is, when you press the button and you got a pin change interrupt, we're just going to say, hey, the pin state should change, but then we're going to use our timer overflow, which is going at a relatively slow 120 times per second.
Yeah, 8 milliseconds.
To sort of say, oh, the button wants to change, all right, I'm going to do that.
Now note that the timer overflow could hit right after the pin change interrupt. So you can do things where you have like another variable that counts, and maybe it needs 5 timer overflows before you do this.
And we could actually do that, just say pin change, actually pin change equals 5, and then right above it say pin change plus plus. If pin change, and if pin change does not equal 0, pin change plus plus. So now what we're doing is the button basically starts this contraption going where if you press the button, the value is now 1. And then the timer is going to methodically increase that value once it becomes 1 until eventually you say, okay, after 5 iterations, that's probably safe enough that you're not going to see any accidental bounces. And what's fun is that anytime the button is bounced again, within this time, the button goes back to 1.
Yeah.
So that you are sort of guaranteeing that after the last time the button sort of toggles state, it's going to wait 5 timer overflows before actually changing the state. So that's sort of what our logic is. So this is sort of a little bit of
It's a little
squirrely
bit of
stuff.
a Rube Goldbergian contraption in code to make it behave.
Now, if I had something like a system time, like if we were doing this on a computer, we could just say, what is the time now? Anytime someone pressed the button, we would just say, oh, the time is now, and then we'd have this last button press, and just say, if the button press is within too short of a time since the last button press, just ignore it.
But we can't do that, so we use a timer.
That's what
Timer
we're sort of
useful.
simulating.
And yeah, it's totally
Let's see if this
legitimate.
works.
Yeah, sure. It's totally legitimate, I think, to use a timer that you're using for something else and just put in, as long as the piece of code is fairly short and executes quickly, which a couple of if statements will, it's totally legitimate to do that kind of thing.
Well, it still works.
Yeah.
That
Still works as a button, so that's good. All right, that is it, I think. Any questions on any of this? Any more questions? Or general questions about like layout? Yeah.
What's the maximum dimensions of the board?
4 inches by, 100 millimeters by 80 millimeters. However, that's only the dimensions of the board, of all the copper on the board. So if you need something to jut out, you technically can, as long as it has no copper on it. But that's only for mechanical.
I don't know if it's explicit, it should be explicitly in the instructions, but for your layout, we are looking for the most compact board that can be reasonably made. And there's sort
Unless
of,
you have a good reason, like mechanical or housing reason, to make it bigger than it needs.
in general, we see there's usually 3 kinds of boards we see. One are people who really sat there for hours and hours and made this crazy compact thing because they enjoyed making it. And it's really cool and they say it looks great. There are other people who make something that's reasonably small, clearly is a pretty small size. They didn't maybe cram everything into both layers and have parts on both sides to make it harder to solder, but it's a pretty small board. And then usually we get a couple people who, there's the default board that shows up when you first start on Eagle,
That's what they give.
and that's what they give us with like parts slapped down. It's either the auto router or the auto router's brother, you know, that sort of shoots the stuff out, and we say, okay, this is the largest board you could make. You needed about a tenth of this space for your 7 parts. You know, you didn't put a lot of time into it. Usually, and there is a sort of a, when we used to have people, your lab fee already covers making the boards, but the way we used to do it is we figured out how much it cost to make all the panels, and then we figured your square inches out. And the people with giganto boards, they were shouldering most of the cost because that's actually how this stuff is costed. It's by the square inch. So if you have a gigantic board for no reason, you sort of are quadrupling your costs for no reason. And I think most people should have your schematic feedback. I think we're starting on the secondary and tertiary feedbacks. So if we aren't responding to you, you may want to just ping us because we're sort of going by like Dropbox dates, which if we already looked at your file because you got it in early, but then you gave it like the very same day, it may just be on our cutoff.
For the sort of unofficial submissions, if you have a question like that you're emailing to us anyway, just attach the schematic because that's the easiest thing for those.
It's easier if it's in Dropbox. Actually.
Okay, fine.
But you can
Do
attach
both.
it. Do both. Version numbers are also very helpful because, right, you have the same file and you just update it, but then it depends on who's looked at it. This is sort of chaos going on basically on the grading side where it's like, I don't remember, did I look at this one? Did Tom look at this one? If I look at the ones from this time window to this time window, but then someone updates it in that time window, like, you know, just chaos ensues. And so if your board is not being looked at, just ping us because it may have just, you may have updated it and things that confused.
Are we allowed to, apart from our board, right, are we allowed to use per board with like that's array LEDs on is actually
That's probably fine if you are making an array of LEDs. So another thing, if your gadget is really better suited as like 2 small boards, one with a bunch of stuff on it and a connector to your board, it's perfectly fine. You can create 2 separate equal projects, have 2 schematics and 2 layouts, and just remind us that you have 2 boards, and we just throw them on. So for instance, if you want to have a cool LED pattern, just make it an eagle because it's a lot easier than perf board, or at least that's what I think, maybe. Because you can put them in, you can rotate parts on 90 degrees, you can do 45 degrees.
You
You
can
make
make
a spiral.
rotate, you can do rotate 30 or
So you can do a spiral of LEDs if you wanted, and then just have the 3 or 4 pins.
just connected to it all.
Yeah, so you need one, in your example, you need one schematic that has a ton of LEDs, maybe some resistors, and then a connector that it probably has power and ground, and maybe a MOSFET control pin or something. And just a pin header 1x3 is probably fine. And your other board has that pin header 1x3, and that's it. That's how the 2 connect.
And if I was trying to get really bright, it would be like, LED on that mini gadget.
That's in the library.
That's not very good. I'm trying not to use, I'm only trying to use blue color. I just use that LED or, nobody can go there.
If you only want blue, you could probably just use the LED, there's a 1206 LED.
Yeah, but don't pretend, I'm just right now.
We also include 3mm and 5mm.
I believe there's 3 and 5 millimeter LEDs. LEDs are really bright nowadays. Like this is not a special LED. This thing is like 80 cents. A 1206 LED, you could probably get one that's alarmingly bright. I haven't inspected one because I haven't needed one, but the size of it, like they're not 1 watt LEDs, right? You can buy non-eye safe LEDs nowadays. I'm not even sure these are eye safe, to be honest. Don't put them up here.
So we can't use doable LEDs.
I believe
There should be a 3 and 5 millimeter LED in the LED package.
And it's very easy to find extremely bright 5 millimeter LEDs. So if you want to go that route, that's fine. LEDs, they don't always have to be surface mount. Like for aesthetic reasons, it's, sometimes the through-hole LEDs just look better.
Yeah, I think the only things that, some people have been using through-hole LEDs, that's fine, connectors or through-hole. The only things that we kind of like, some people have been using the giant 7805 regulator, the giant 3-legged regulator, the little SOT 2231, the little one that, the picture is bigger in Eagle, but if you look at the scale, it is much, much smaller. For I think almost all of you, it's going to be plenty fun. So I don't recommend the giant through-hole regulator for anybody. All right, well, that's code. We look forward to some layout drafts on Friday. But before you give us a layout, try to get sort of the okay or like, sort of the diminishing returns. So those of you who've done multiple feedbacks,
There's like one.
probably you'll notice that like our recommendations become less and less dire. And it's just sort of like, well, you could put this on a different pin if you wanted to blink the LED. And you could just say, I don't want to blink the LED and move on with it.
Or like change this resistor value. You can go on to the layout
Yeah.
if that's your
Yeah.
feedback.
All right.
Assignment 6th grades have been sent out by now, so check your email, and if you haven't gotten anything, email us and let us know.